Okay, are we having fun so far? Did we learn anything?
It's important to do local analysis.
What was that?
Always do local analysis.
I've had to regroup now because I've prepared far too much and I won't be able to get through it all. So I've focused on what we can do. I just want to do a bit more of the diluteness asymptotics. Remember, we just got this. Look, there's our H minus. I'll just write it down again. Right, that's the solution. And what happens when Z gets large? Yeah, you get 0. That's what I said. Okay, look, let's do this. Remember, you used to do this when you were in calculus. Binomial expansion. Okay, so this H, which is, remember, the imaginary part of H is the flow in the lower part, it vanishes far away. So this one slot's not doing a very good job at causing a mean flow in the lower fluid. Okay, remember, think of the interfacing as transferring a shear stress over the interface so that it drags the lower fluid, even though there's no plate moving it underneath. Okay, you're trying to drag the fluid. But one slot's not going to do it. But we can do some diluteness asymptotics. We're going to have to do some rescaling, though, to be able to do that. So let me just, I'll just do it again. Look. So let's let Z with two dashes, look, be CZ. So that the Z I've been working with now, when it's equal to plus or minus 1, is capital Z is plus or minus C. Remember, we had 2C as our the interface width. So this means that as a function now of this Z, this is 1 over sigma plus 1, Z over C minus Z squared over C squared minus 1 to the half. Okay? And as I just showed you, if you just expand all this out, oh yeah, I think I must have changed the magnification. There we go. That's a bit better. Okay, then I take out that capital C over C. Got 1 minus C squared over Z squared to the half. I do the binomial expansion again. I get Z over C, Z over C, that's 1 minus C squared over 2 Z squared, plus lots of other things that get smaller. So you can see that this looks like C squared, no, C, because that cancels with that C. These cancel out, and I get 1 over 2 sigma plus 1 C over Z. Plus order turns out C over Z. Cubed. Okay. Okay, which dies off as capital Z goes to 0. So what I'd like to do is to find the effect of a dilute but periodic array of these little slots. Okay. Each one of them causes a 1 over Z far field in the lower half, in the lower fluid. But what happens if I superpose a periodic array of simple poles? Does anybody know? If I superpose a periodic array of simple poles, i.e., suppose I do this. Pick any integer, n, and I add a simple pole at 0, 2L, 4L, minus 2L, minus 4. Anyone? Nobody knows? Demetrius knows, but of course so he should. This is an identity. There you go, mathematicians. Very important identity. Basically, whenever I see COT, I think of an infinite periodic array of superpoles. Okay. Now, here's what I'm going to do. If you think about it, this is like 1 over z plus 1 over z minus 2l plus there's 1 over z plus 2l plus etc. So look, this is the one that's already there. You see, move the c over, I've got a 1 over z. That's, in a sense, the flow that the lower fluid feels because of that one slot centered at the origin. But now, if I add in the effects of all the other slots, I can essentially periodize this by replacing the 1 over z there by this, hence this, by the identity. Everybody see? This is my diluteness asymptotics coming in because to leading order in C over L, I just linearly superpose the individual effects. I'm not taking account of reflections because, of course, there'll be higher order corrections. But to leading order, I just add in the 1 over z effect from all of the slots. Everybody see? So I'm going to replace 1 over z by pi over 2l cot pi z over 2l. This is allowable as my leading order solution. So therefore, H minus periodized is 1, oh, let's put C, look, C over 2 sigma plus 1. And then instead of 1 over z, I'm going to put pi over 2l cot pi z over 2l. Everybody see the little trick? I've just superposed the effect, leading order effect of an infinite array now. Well, this is, suppose there's an infinite wall with one slot. Far down, it just falls off like 1 over z. But now I'm imagining I've got one slot there, another one there, another one there, and infinite. So now I'm just going to linearly superpose the effects of all of those, which is like replacing that by that because of this identity. Another calculus exercise. What does cot look like when z gets very negative in y? Well, I'll tell you. Cot z tends to I as imaginary part of z gets very, very negative. You can just check that calculus exercise. Aha! So now I'm in. Right. So this tends to. Sorry. This tends to pi ci over 4 sigma plus 1 L as y tends to minus infinity. So therefore, W minus tends to pi c, is the imaginary part, remember, over 4L sigma plus 1. Notice that's order C over L. That's my small parameter. So this is small in the far field, but that's because it's a dilute array. But because it's an array, it's having a small forcing of the shearing of the fluid in the far field. Everybody see? So this is order C over L, which is small, but I've managed to periodize using this little trick to find the leading order dragged motion from the upper fluid, yes.
So the first initial solution, did
Yeah.
you say it's a gap with an infinite
Yes,
wall?
yes.
It's not just a gap with the bit directly below or
No,
a gap?
there's fluid, so apart from these two walls, there's fluid everywhere.
Okay.
There's plus fluid, wall, separated from a minus fluid of different viscosity by the interface.
But it does extend...
Everywhere down below, everywhere up above.
So when you're superimposing them,
Yeah.
the bit that's down below of every single solution is just a smaller
Yeah, small.
effect, so you wouldn't...
Yeah, yeah. Thank you. Thank you for your questions. Any other questions? This is cool, right? Notice, I was able to find, by the way, I'll tell you right now, this is actually a pretty good estimate of the drag velocity, even when C over L is not very big, not very small, I mean. Notice how crucial just solving that single slot problem was to finding an estimate actually for quite a large parameter range. Everybody see? So by using the asymptotics in the different directions, we're actually getting quite a lot of control over the flow before we've even done any calculations. All right, any questions about that? I'm going to move on to something that's a little bit different. Okay, by the way, it's an interesting asymptotics exercise to look at higher order effects. So do a higher order expansion in C over L. Okay, because then you have to take into account kind of, you have to do inner outer asymptotics to kind of find the higher order corrections. But the leading order corrections is just this simple kind of periodized function. Who's heard of the, when you did complex analysis, did you learn the Joukowsky map? Anybody know what, anybody tell me what it is? Anybody? You might have seen it in fluids course. No? That's right. That's where it was first used. The Joukowsky transform. By the way, remember what I told you we always do here is we always look things up like our students on Wikipedia. So look, as you were saying, you often use these as a leading order approximation for a flow past an airfoil. It's a conformal mapping that helps you out, and there it is. You're mapping the unit disk, the interior or the exterior, to the exterior of a slit. Okay, so let's consider this conformal map. Oh yeah. I'm going to put a minus sign and a half. It's not. It's just a rescaling of what you see in Wikipedia. Let's think about the image of the interior of the unit disk under this mapping. Where does the origin go to? Well, when z is equal to 0, 1 over 0 goes to infinity, right? So the image under this mapping of this shaded region here includes, so I'm thinking now of a z-plane, and I want to know where every point in here goes to under this functional correspondence. It obviously goes to the to far away. Okay? And then what does the unit circle go to? Huh? Well, that's one point, yeah. So look, if I pick that point, I get 1 plus 1 over minus divided by minus a half, or times minus a half. That's minus 1.
Yeah, minus 1, yeah.
And then where does this one go to? That's
1.
That goes to 1. And then what about every point in between? Straight line. it actually goes, watch me everybody, this is what happens with these things. If I go from +1, which is this point, to the dot over there, I basically go, imagine I go across here. Can you see my I'm doing it all at once? Yep. And then I'm going to go back the other way. But I stay on the same slot, except I kind of come on the I think of it as the underside. So I cover the slit twice when I go around the circle once. And you can think of those as the two different sides of this airfoil. Or for us, we're not interested in airfoils. We're interested in multiphase flows. So we're going to consider this to be like the top side of our interface when you come plus down, and the lower half circle as you come the upside. Does everybody see? Let's just check. Have I got any other coloured pens? Let me see. Where does this go to? Well, look, 1 is there, and 0 is infinity, so I bet, and by the way, if I evaluate anything real on here, zeta's real, and 1 over z is real, so it's going to be real, so it's going to go along there, look. And then if I go through infinity, watch me everybody, I'm going to go through infinity, I'm going to go through infinity on the Riemann sphere, come back over here, and I'm here. Okay, that's the real diameter. So in our problem, what does the real diameter correspond to? I'm still talking about the single interface, the same problem from last time. No. The diameter, the real diameter corresponds to the no-slip walls. Yeah? And then if I've got a point here, look, that's like a point there. And if I've got another point there, what do I want to do? Like that? That's the kind of underside. Okay, let's call this C0 plus and C0 minus. Okay? So this is the upper side of the interface. And C0 minus is the lower side. You see, Tchaikovsky airfoils, it's not just about Tchaikovsky airfoils. That's one thing you can do, and then you did that a long time ago, but it's still useful, even for us. So this region then, the upper half disk, is going to be my plus region, my plus phase, and this one's going to be my minus phase. Okay? And what's very interesting is coming in from the two sides here, look, is basically evaluating here and here, where this is actually the complex conjugate. So if this is a point, let's call it zeta star, then this is zeta star bar. Okay? So zeta star and zeta star bar on the unit circle map to the two sides of the interface, but from the plus and minus respectively. Any questions? What would you do if you wanted to map to a vertical slit? You want to map the same region to a vertical slit. A vertical interface, whatever. Huh? The imaginary part of what?
The disc. Then you'd go on to the imaginary part of the Z.
No, so here's what I'm asking. So this circle, look, maps to a slit and back. I want the same circle to map to a slit and back that's vertical. Okay? Oh, actually, maybe I should color the bottom in a different color. Oh. Any thoughts? Very good. Okay, so you just said multiply by I. Does everybody remember that multiplying by I rotates things by 90 degrees? You could do that. That would be a perfectly viable map. Can anybody think of another one? The reason I don't like that one is because if I take this and multiply by I, my pole at the origin changes from residue minus a half to minus I over 2. And I'd like to enforce the same asymptotic condition that it goes like minus 1 over 2 zeta. Okay? So I'd like it to have this same asymptotics, but this obviously maps to the real line. How about this? Well, let's keep the 1 over zeta because I want that. Oh, you can't see it. You can't see it. I want the 1 over zeta, but because I want it to have the same asymptotics as my Joukowsky map. What if I change the sign? Notice, by the way, that if I'm on this circle, that's mod zeta squared is equal to 1. That's the equation of the circle, and you can write that as zeta zeta bar. So on the circle, zeta bar is 1 over zeta. Right? So look, if I take the complex conjugate of this term, I get zeta. And I'm subtracting zeta, which means that this is going to be purely imaginary. Notice here, I took 1 over zeta, and I take a complex conjugate of that, I get zeta if I'm on the unit circle. So I'm adding its complex conjugate, which is why everything's real. That's why I map to a real slit. Everyone see? So this one, if I put the plus zeta, I map to this real slit. If I put the minus zeta, I map to this slit. It's just a different Joukowsky map. Everyone happy? I'm just going to write these down on here because I don't want you to ever forget. Okay, you might have seen that before in, by the way, who's heard of Chebyshev polynomials? And you don't know what Joukowsky is? This is cosine theta. This is the first Chebyshev polynomial. And if you put n there and n there, that's Tn. Just for your information. This is a school after all. Okay. So here's what I'm going to do. I am going to, remember we kind of got the answer to this single slot problem by accident. I posed an ansatz, came from the local analysis, enforced far through boundary, and I got it. I'm going to get it for you another way. And then later I'm going to get it for you a third way. Well, that mapping's Z, right? So I'll keep that there in case I need it again. So let's introduce the same complex potentials as before. And what I'm going to do is I'm going to put a capital H of zeta to be, watch me everybody, H of Z, H plus, this complex potential, with the Z zeta. If I compose analytic functions, I get another analytic function. Okay, so Z was an analytic function zeta apart from the pole, and then I'm going to compose it with an analytic function of Z. So this will be composition of analytic functions. So H plus will be analytic function, and H minus again, that was what we did before, and H minus will be the same thing. Okay, so I'm composing analytic functions. I'm taking the complex potentials and thinking them now as functions in the zeta domain. Everybody see? Geometrically it's easy to think. Look, here I've got H plus and H minus. We already know what they are, we found them. But suppose we take a point Z there and map it to there, and then evaluate H. That's H plus of zeta. Okay? It's a pullback. People call it a pullback. Okay? I don't. I just think that's unnecessary terminology, but you might hear that somewhere else. Okay, now what I'm going to do is try to find these. As I said, we already know what they are, but we don't know what they are as functions of zeta. So that's what we're going to do. So on zeta bar is equal to zeta. This is the real diameter. Am I still on the board? Yeah. W plus is equal to W minus is equal to 0. There's no slip. This implies the imaginary part of H plus is 0 on zeta bar is equal to zeta. Okay? Which means that this minus its complex conjugate is 0. I can write that as people don't tend to, I didn't see this when I was an undergrad, which has surprised me. Has anybody seen this notation? If you give me an analytic function, in this case capital H plus of zeta, every analytic function has a Schwartz conjugate function, which is usually denoted with a bar over the function name, which is defined by this. Notice, if you've given me H plus of zeta, just a function of zeta, then I can certainly define this thing, right? Because I know what H plus of a complex variable is, and then I conjugate the answer. So you can think of this plus kind of falling through here, that leaves a plus on there, and that conjugate just goes back to the zeta. These are called Schwartz conjugates. People don't tend to learn about them, I've noticed. Okay, but they're very important. I think that's one of the reasons is because a lot of the elementary functions you see in complex analysis normally have the Schwartz conjugate equal to the same function, so they kind of don't arise. But they're going to be very important for us. Okay, so this is the definition of what I mean by H plus. So look, I know this is minus this is 0 on here, which means that this is equal to this on there. But then zeta bar is equal to zeta when this is true. So this top thing can be used to say this. So in other words, I've just shown you, look, that the Schwartz conjugate of H plus is the same as the original function. Everybody see? You need to keep track of these things. This comes from the boundary condition, and then I'm on here, which means I replace zeta bar by zeta, and then this function defined by this is actually equal to the original H plus. And similarly, you can show that H minus bar zeta is equal to H minus. So I've just shown that these functions have the same Schwartz conjugate using the no-slip condition. Okay?
Is the second one that is an identity to analytic function?
No. This one?
No, the one below.
This one, yes. In other words, if you give me an analytic function H plus, I define its conjugate H plus bar by taking H plus, evaluating at a point zeta bar, and conjugating the whole result. Let me just give you an example. Suppose H plus, well, let's not use H plus, let's use F. Suppose I just introduce that exponential function. What's the Schwartz conjugate of F? Everyone's doing it in their head. I'm going to do it for you. I'm glad. I saw you were working, so you get full marks. Right, here I'm going to do it. This is the identity. So what I'm going to do is I'm going to do e to the I zeta bar. That's f of zeta bar. But now I conjugate the whole thing. So I've just given you a function whose Schwartz conjugate is not the same, because the plus has changed to a minus. So those are Schwartz conjugate functions, but they're not the same. Okay? It turns out in our problem, we don't have that property. They both turn out to be the same, but that's only because of the no-slip condition.
And so is that only valid at the diameter?
Very good. You're on the ball here. No, there's something called analytic continuation, which means that if you find an identity between analytic functions that's valid on certainly a dense curve like this. But you even only need an infinitude of points, discrete points. It's P-guard theorems. It's the same everywhere. It's called analytic continuation. It's one of the reasons why I fell in love with complex analysis, because I couldn't see anything more powerful in my whole undergraduate math degree. How does that happen? Here we certainly have it's a continuum of points. It's a whole line. We've got this true. It's an identity between analytic functions. It means it's true everywhere, where you can continue off this line. Okay.
Even though row bar doesn't equal row off.
Right. I'm glad you're looking amazed or confused at the moment, because you absolutely right. Does everybody understand? I've taken something that's valid on a line where zeta is zeta, zeta bar is zeta, found of something that's true between two functions of zeta on there, but because they're both analytic functions on that line, you can continue that relation off the line everywhere it can be continued. It's absolutely remarkable. And you never see that in real analysis. You have to work much harder for everything. All right, so anyway, we've got that. We haven't even done interface conditions yet. So watch me, everybody. So what about the interface conditions? So we've got W plus is W minus, right? And mu, no, I'm going to do sigma plus is chi plus is chi minus, right? There's my interface conditions from Cauchy Riemann before. So, by the way, the other thing you can use. I'm just going to pause here. So H minus is analytic in here. Remember, we know that's true because that's where is the complex potential of the flow. But we've also got that H minus bar is H plus, H minus. So they're the same. And this is actually, has anybody heard of Schwartz reflection principle? So here's what the Schwartz reflection principle says. If I've got this region of analyticity, but then I've got the Schwartz conjugate equal to itself, so it's like it's real on here, you can reflect into the upper half and it's also analytic there. It's like method of images, but there's no poles. Okay? So this is Schwartz reflection principle. So in other words, I can argue, I'm not going to go into the details, I don't have time. So Schwartz reflection principle, based on this no slip condition, implies H plus and H minus, it turns out, are analytic in the whole disk. Except H plus has a simple pole at the origin. Why is that? H plus is H plus of Z, remember? And H plus needs to go like Z as Y tends to plus infinity. Now, what does Z look like as a function of zeta at infinity? Remember, zeta is equal to 0 is the preimage of infinity, so when this gets large, this function goes like minus 1 over 2 zeta. Right? So this goes like, means that H plus look goes like minus 1 over 2 zeta. Okay, so H plus actually is analytic in the whole disk except for the simple pole. H minus is analytic everywhere in the disk. Okay, let's get on with our boundary conditions. Oops. So let's just do that one. That means that H plus of zeta. Now watch. This is the imaginary part W plus. I've got to set that equal to W minus, which is the imaginary part of H minus, but coming in from the bottom. Or in other words, on the lower half of the circle. So in other words, I need H minus at zeta bar minus its conjugate. Does everybody see? Look, I've picked a point on the upper circle and worked out the imaginary part of H plus, but that's coming from the top. Now I need to come from the bottom and match with the W minus there. That's the imaginary part of H minus, but evaluated at the conjugate point. You got it? So all I've done is I've moved the bar through the whole thing, so that gives me the conjugate H minus, and then that becomes zeta. Okay. And then I also get, for the other boundary condition, I get this. Oh. Okay, this is the same thing, and now I evaluated the zeta bar, and then I've taken the conjugate. I'm just going to write these down. I'm going to reorganize these. Oh. This is just reorganization. And I've used the fact that zeta bar is 1 over zeta on these circles. Okay? Now I'm going to introduce two new functions, h plus of zeta plus h minus of zeta. That's a linear combination of the two things I'm looking for. And then there's going to be g. Okay. I've taken h plus and h minus, just added them up, and then I've taken h plus minus sigma h minus. Can you see why I've done that? Well, that's just f, isn't it? And that's just g. Now what's this? Remembering that I'm on the unit circle. Well, 1 over zeta is just zeta bar. So that's h plus of zeta, h plus bar of zeta bar. This is plus h minus bar of zeta bar. Isn't that just the complex conjugate of that? And then this is g. And on the unit circle, this is just minus the complex conjugate. So the interface conditions tell me what? Don't they tell me that the imaginary part of f is 0 on C naught, the unit circle? Okay, that one. And then this one tells me that the real part of G is 0 on C naught, on the unit circle. Right? Tell me about the singularities of f and g inside the disk. Well, here's the definitions of f and g. I argued that h minus is analytic everywhere in the disk. I told you that h plus has a minus 1 over 2 zeta singularity. Was what I was doing here. That was just this bit. H plus has this type of singularity. Since there's a bit of H plus in both F and G, both of them have the same minus 1 over 2 zeta singularity inside the disk, but are otherwise analytic. Everybody with me? We're nearly finished. These are two F and G. They've both got the same singularity at the origin. The real part of f, the real part of g is 0, the imaginary part of f is 0. And they both have the same singularity at the origin. Remember what this one was? This maps unit circle to that real slit. This maps to that. What's true of the imaginary part on here? 0. What's true of the real part on here? So guess what? And by the way, look, they've got the right singularities. So f and g are just these two functions, these two Joukowski maps. So in this two-phase problem, the potentials you're looking for turn out to be linear combinations of horizontal and vertical slips. Joukowski maps. Everyone's looking a bit bemused. Hence, so this is the deduction, hence f of zeta is, let me get this right. Which one's which? Ah, yeah, f of zeta is z. R of zeta, where these are these functions here. Okay, and by the way, you can solve these to show that H plus, of course, is sigma f plus g, just simultaneous equations. So if you take these expressions, which just come from solving these, you take these answers, where these are these slip maps, that's the answer you're looking for. I'll give you the final results. So some simple algebra, simple, it is simple, it's just literally coupled equations. Thoughts? Those are the answers. That's a sigma minus 1. By the way, that method I've just shown you is not very well known. I was just using Schwartz conjugates and a symmetry assumption. Well, it wasn't a symmetry assumption. I was using a very crucial fact here in this step. That the pre-images of the two sides of the interface are complex conjugates of each other. That's why there's a zeta bar there and not a zeta. That's a very subtle thing. And I think I only know of one paper in the literature. It was a porous media problem where somebody used this trick. So this trick is not very well known. But I like this trick because look at the answers. There. Written as a function of this zeta variable in the unit disk, I've got, by the way, if you want to plot streamlines, constant contours of constant vorticity, velocity, these are the thing to do, because all you need is to grid the disk. Grid the disk, get MATLAB to work out the constant parts, imaginary parts, and plot. Okay. Much easier than gridding a semi-infinite region with a gap. Come on, does something strike you about this? Notice, by the way, that this is just zeta with a constant multiplied by a constant. So as you go to infinity, zeta goes to 0. But that's consistent with, remember, the H minus going to 1 over, looking like 1 over Z as you go down below. But what's the other most striking thing about this? What was the first thing I did today that involved some calculations? It's getting near lunchtime, everyone's falling asleep. Well, didn't I do a local analysis of the singular points and find square root branch points? So what are you all thinking? Where are they? There's no square roots here. Look, I love this. I'm being dramatic here because I don't think enough people really appreciate this. I have got a representation of the solution, a parameterization, or as the mathematicians like to call it, a uniformization of the solution that has factored in the singularities so that they're naturally in there, but you don't see them. There's no there's the square roots are in the z-plane. But when I use this parametric zeta disk, they've been uniformized. They're points of analyticity now. Now you're all staring at me. I don't know if that's because you're bored or because you're as amazed as I am. You can't see the square root branch points. They've been uniformized by my choice of parameterization. How could I check that this gives the same answer as before? Huh?
Substitute in the match.
Yeah, look. Look at this. I'm going to do this on the board here. Let me multiply up by minus 2z, look, is zeta plus 1 over zeta. If I multiply up again, I get zeta squared, what, plus 2z zeta plus 1? What's that? Quadratic equation with coefficients that depend on z. So zeta is minus 2z, minus b plus or minus 4 root squared. Plus or minus, I'll decide in a minute, 4z squared minus 4 divided by 2. Which root do I take? Remembering that I need zeta to go to 0 as z goes to infinity. The plus, so that this will cancel with that. Oh my goodness. Oh my goodness. If I substitute this into there and there and there, I'll get what I found earlier using the local analysis in the z-plane. My square root branch points are in the uniformization. When written as a function of zeta, you never evaluate a square root. Which frankly, even if you do numerics, is a bonus, because I can't tell you how many times I've spent my half a day just making MATLAB or Python pick the right branch out. So if you can do this, there's significant advantage in that. And by the way, it builds in the singular behavior. It's built in. Everybody see? You okay, Mark? You looking? By the way, did you notice what I did there? I hardly did any work. I used the powerful notion of analytic continuation, okay, off the boundaries, and it basically allowed me to just do algebra to find the functions. Of course, the key step was noticing that I've got this conformal slip map structure. Okay. Any questions about that? Okay. I'm going to have to cut it short now. I'm going to have to decide what to do. You know what? I'm going to show you the following thing because I think it's good for you to know. Yeah.
So that solution, you don't need to think about periodic domain.
remember, this is just the single slot. It was just a rederivation of the single slot case.
So do you have to do it again?
If I want to do the periodization, yeah, I can do it. I can do it.
Just do
Yeah, that's just the next step. That's the diluteness asymptotics. Yeah. Does everyone see what I just did? I just rederived the solution I kind of got by magic, but actually using Schwartz reflections, Schwartz conjugates, and slip maps. And by the way, I know there's a whole bunch of problems that you can solve like this, multiphase problems using these ideas that just haven't been done yet. Because I don't think anybody, by the way, the paper that I got this idea from is, first of all, about 40 years old, and it's got like 6 citations. So people don't know how to do this. Just want to show you something else. It's another, I haven't got much time left, so I'm just going to quickly go through these things. Like, here's my single slot domain again. Let's think about that. By the way, what type of mapping is this? Remember, this is what we call a Joukowsky map. What type of mapping do we call this if you define a linear function over a linear function? Mobius, or linear fractional, yes. So can you see what this domain will go to? What do we know about Mobius maps? Huh? Yeah, well, one thing that's true of Mobius maps is they map every circle to another circle. Okay, that's easy to prove. I'm just going to show you, actually, I'm just going to tell you what the answer is here. This maps to the following thing. Well, by the way, let's call this R plus and R minus, the two sides of that wall, and this S plus and S minus, and this is my interface. I'm just going to write down the correspondences here. And you can check for yourself that I'm right about this. Okay? So the interface between plus and minus 1 maps to the whole real axis in this chi variable. So this is chi. The top wall, semi-infinite wall, is mapped to this finite slot between minus 1 and 1. The lower wall to the same thing, but with kind of the other side, and then this is mapped to there. Everyone see? Easy to check. There's a little exercise. What happens if I take a logarithm? That's the origin. Over here, what's the argument? Zero. So the imaginary part is 0. And log chi, well, what happens as chi comes in here? Look, modulus is very small. Log of something very small is very negative. It goes up to 1, where log of 1 is 0. And then log of 1 over here gets very large and positive. So actually, this semi-infinite line in this plane maps to the whole chi-axis. Everyone see? What about this? What's the argument on S plus? What's the log? What's the range of the log between 0 and 1? It's negative, isn't it? So there's S plus, there's R plus, this is pi, and then what's the argument here? Minus pi, so it's down here. So eta, which is log of 1 plus z over 1 minus z, what has it done? It's mapped my fluid domain. Oh, by the way, I forgot to mention, of course, that this, you can check that maps to plus and this maps to minus. I've mapped my two fluids to strips. Why should we be excited about that? What do you think about as soon as you see a problem in a strip? Yeah, strips. How do we do analysis in strips? Who's the magic name? Fourier transforms. Whenever you do have a problem in a strip, especially for analytic functions, you should think Fourier transforms. Everyone, nobody else seems to, are you okay? You see Fourier transform? Yep. So I've just, by virtue of this mapping, I can now find h plus of eta, h minus of eta in these strips using Fourier transforms. Has everybody seen Fourier transforms before? All right, well, I'm going to, still got 20 minutes. Do you know what I'm going to do? I'm going to give you a really cool derivation of the... Who hasn't seen Fourier transforms? Be honest. By the way, if you've seen them, which you all have, because nobody put their hand up just now, how did you derive them? I'm going to show you, because I've only got 10 minutes, I haven't got time to do a full calculation, so I'm just going to show you something really cool. This is something I did about 15 years ago. I'd like you to imagine that eta is some point there, and eta prime is on this, is on that line, that horizontal line, and eta's above it. So what can you say about the imaginary part of eta minus eta prime? It's positive. So if eta and eta prime are in a configuration like that where eta prime's on a line and eta's above it, this is true. So what's this integral, if that's true? Notice I've taken the range on the k integral. It's just the exponential function. What's the integral of exponential function? It's this thing divided by I eta minus eta prime, right? The only thing I have to worry about is, does the damn thing converge? I need the upper range of integration to be finite. But look, k is positive, there's an I there, this has positive imaginary part if they lie like this. Did we see? So what I've got there, look, is I'll do it over here, ik times, let's call it x plus iy, where y is positive and k is positive because I'm on this interval. So that means that this thing has, the only thing I care about is the real part, because does it explode or not? I get e to the ikx, who cares, minus ky. But k is positive and y is positive. So I don't get anything from the upper limit. Let's just do it. It's e to the ik eta minus eta prime over I eta minus eta prime. And I think, correct me if I'm wrong, I get the minus sign because it's everyone happy? Okay. Suppose I had some line like that with eta on it, and eta was down there. Notice I've swapped the sign. I can do all the same things, except now what I get is minus 1 over I eta prime minus eta. It's the same thing because I've arranged it because now imaginary part of eta minus eta prime is negative. So I've swapped the sign of k here by putting that minus sign in, and I've got that. Everyone happy? Elementary. Elementary. I'm going to need this. Who's heard of Cauchy's integral formula? Suppose I've got a strip. And by the way, I'd like to think of the strip geometrically. Watch, everyone, watch. Here's my strip. And that's what I'm interested in. There's my point eta in the strip. What's Cauchy's integral formula? If you give me any bounded domain, if you give me any domain, it's the integral of h of eta prime d eta prime is 1 over 2 pi. That's Cauchy's integral formula. By the way, pi I, sorry, yeah. Thank you. You see, he's a boundary integral person. He's a boundary integral person, so he knows there's 1 or 2, because boundary integral methods are all based on this representation. At least if you do two-dimensional problems. Okay? So actually, I could just use this to form a boundary integral formulation to find my h plus and h minus. And then I'd couple the two strips. Let's call this L, and let's call this L hat. Then I'm going to write Cauchy's integral formula like this, just separating the two parts. It's just two parts of the integral, two different contours. Everyone with me still? Everything's elementary. I'm using Cauchy's integral formula. What do you think I'm going to do next? I noticed, by the way, if I'm here and eta prime is on L plus, I can use that one to replace my Cauchy kernel as an integral in a spectral parameter k. And if I'm not down here on L, it's supposed to be L there, I'm in this situation where I can replace my Cauchy kernel by that. Isn't it beautiful? I've found an elementary relation as an integral in K of this Cauchy kernel. I'm using a geometrical fact that the strip is the intersection of something that's above and below a half plane. And and everything's uniformly convergent, so I can substitute the integrals, swap. I get a transform pair. It's called the Fourier transform. I love that because most treatments of Fourier analysis I've seen rely on, you take Fourier series, and you take some limit as the period goes to infinity, requires lots of. This is just geometry and basic observations. I do have to use Cauchy's integral form. But that's the non-trivial result. Do you want me to go on? I haven't got much time, but basically, here's what you do. By the way, there's a paper of mine in CMFT Journal in 2015. It's called Fourier. If you want to see this done carefully, Fourier-Mellin transforms for circular domains. If you want to see it all done properly, but I've just given you. I mean, let's face it. You could show this to undergrads once they've seen Cauchy's integral formula, and you've got the Fourier transform right there. It's the complex Fourier transform. But that's it. And then, so all you do then is you substitute, in this one you substitute there, and then this one you substitute there, and I'll let you do the calculations. It's very easy now. You just get that h of eta So this is known as the complex Fourier transform pair. So this is usually called the Fourier transform of H. And if you want to reconstruct H from its transform, you use this inversion formula here. Okay, I'm out of time, but let me just finish. The reason I've shown you all that, and I was going to give you some more details, but of course I knew I wouldn't have time, is because in this paper, what we're able to do is remember, one thing you've learned is the importance of the single interface problem. Now remember I showed you those grooves. So this was an interface. This was no slip. This was the bottom of the groove, no slip. What we did is we used that chi transformation I just showed you to map it to two strips. And then we used the complex transform I just showed you. Did all the same things, and we were able to get analytical solutions for H plus and H minus. In the groove, H minus now is not the symmetric lower half plane, it's this small little groove here, full of viscous fluid with viscosity mu minus. But then there's mu plus. But we can solve it using these transform methods in here and find analytical solutions to the single phase problem, single entity, single groove problem. And then we combine it with the diluteness asymptotics I've shown you and the height asymptotics to do what I said earlier. In other words, we get rid of this using diluteness, we get rid of this using height asymptotics, we solve that two-phase problem using this transform method here. And we're able to get estimates for the drag, how much it gets dragged and things like that. We can even include pressure gradients in grooves. So, for example, a lot of people are interested in blocking off these grooves. So that you see, you've got a shear flow over here. It's going to drag the fluid out of the groove unless you block it. You don't want that because you want the lubricant to stay in the groove. So what you have is finite end groove troughs, they're called. And then that means you need a back pressure to keep it in the groove. There's a recirculation in the groove, but we can resolve that too using these transform methods. So that's what we did in the paper I just showed you. I would have liked to have given you more details of that because the analysis is really quite nice. Let me show you one more thing because I've got 2 more minutes. This would be a nice way to tie the whole thing together. I'm going to show you what look, I worked out all the details for you for our problem. But I'm just going to write down the final answer. If I can find it. Yeah, look, this is the inverse transform. Here we go. So analysis that is omitted. Don't need to worry about the details, but I'd like you to look at the denominators.
You need to zoom out.
Oh yeah. Okay, this is a nice place to finish. We're able to show, I wasn't able to show you, that for the H, I think it's the H minus or H plus, I can't remember, but whatever the H plus is, this is going to be this, we show it's equal to this. It's the transform of the solution. So if you want to know what the H is, you put it in the inverse transform. Anybody notice anything about this rho K, the transform? And remember, all I've done is I've taken basically the single phase problem. By the way, this isn't what's in the paper. This is me. I was going to do this today. Too ambitious. Derive this for you as a transform solution of the thing we've been doing all morning, the single interface problem between two symmetric fluids, and you get this. What do you notice about the denominator of the transform? Both of these terms have cosh pi k, sinh pi k. Ring any bells? That's sine pi lambda, sine cosine pi lambda. But notice I've got an ik times eta. And e to the eta, remember, eta was log of z plus 1 over z minus 1. So e to the eta is z plus 1 over z minus 1. So e to the eta times ik is z plus 1 over z minus lambda to the ik. So that's lambda. In my local analysis from earlier, so I'm going to get, so what's going to happen is, look, what happens when either of these is 0? These are, so cosh pi k is 0 when cos of lambda is 0. Sinh of k pi is 0 when sine of lambda is 0. There's going to be poles in this transform, which goes in here. So when you learn how to do this Fourier analysis, right? You're trying to do a long integral line. You close in the upper half plane, and you're going to pick up poles, residues at the poles. And those residues at the poles are going to be precisely at n pi. In other words, exactly what we found earlier. Here, but without doing all the transform analysis. So in other words, the local exponents that appeared in the purely local analysis from a couple of hours ago are the poles in the Fourier transform. As you expect, and then when you do the inverse transform and have to close in contours, you use the residue theorem and you pick up all of those residue contributions, giving you those power laws that you got from the local analysis. Okay? You might have seen that before in complex, well, when you're doing transform solutions of PDEs. Okay. The other thing, the final thing to say is that, of course, this is a special solution for the nice problem I've done today. But if you've got those more complicated groove geometries, the transform methods have the advantage that it picks up all of those local singularities in the rho K. So you kind of don't need to do the local analysis because it's already built in. And it includes the angle data and all the boundary condition data. So in a sense, you kind of avoid having to do the local analysis because the transform solution builds it in. Okay. Then again, this zeta approach from the disk also built it in. Okay, I was far too ambitious with the things I told you, but I at least got through the main ideas. Main ideas are local analysis is very important. Two-phase, everything today's been a two-phase problem. Notice everything today's been linear. Even with linear, two-phase, mixed boundary value problems in complex geometries, they're not so easy to solve. But there are techniques if you combine complex analysis methods with asymptotics. So that's the thing to bear in mind. I think I'll stop there. Thank you for listening.